Thank you. I thank the organizer for letting me talk here. I will talk about work which I have done together with Markus Ruse, also from Geneva. And it concerns the dynamical Casimir effect in brain worlds. It's probably a bit a shock compared to the previous talks. On the other hand, I think we will have more of this as the conference goes on, because as cosmologists, usually we have two ideas in mind. One is we would like to determine the properties of the universe. On the other hand, we don't. This is not a goal for us per se, but we want to learn something about physics by doing so. And something which we would like to know better, and where cosmology might be one of our few, if not our only chance, is the physics at very high energies. And the physics at very high energies, one contender for the physics at very high energies is string theory. And it would be interesting to see whether we can somehow infer some observational consequences of models which are motivated from string theory in cosmology. And that's what this talk is about. So I'll give an introduction, relatively brief, and then I'll talk also very briefly on anti-de Sitter, five-dimensional anti-de Sitter background at low energy. I will discuss the evolution of tensor perturbations in this background of gravity waves. Then I will quantize the linearized Lagrangian for gravity waves in this background, and will calculate particle creation in due to the motion of brain in alien space. And finally I will conclude. So as I said before, string theory is a candidate, the one which people talk most about, so let's call it the most serious. Whether it is true or not is one thing we would like to find out. But the problem about string theory is there is a lot of theory and very little contact with any data. And usually one goes a long way from string theory to make contact with data and neglect so many things that at the end one has a toy, Mickey Mouse toy model, as the one which I will present here is probably a very big oversimplification, might have nothing to do with reality, but we have to try something. So string theory predicts the existence of brain worlds, predicts the existence of hypersurfaces or lower dimensional manifolds in the high 10 or 11 dimensional manifold on which standard model particles are confined. In a kind of minimal version of these models, the only particle propagating in the bulk, in the full space-time, is the graviton. That's what we shall assume here. It's of course tempting in this context to model the expansion of the universe by just the brain sweeping through a spatially non-constant bulk space-time. And that is what we shall do here. That's what one calls motion through a warped bulk, so where the bulk space-time is not constant in the extra dimension, and therefore this induces a time-dependent metric on the brain. Here I will become even more specific, and we will maybe discuss at the end what of the conclusions which I will draw can survive to more general brain worlds. I will assume that the bulk is a five-dimensional anti-de Sitter space-time. This is the so-called Randall-Sundrum model. They were the first to propose this possibility. And our four-dimensional space-time is a brain moving through it. Now, if we had some grain moving through a higher dimensional space, then that induces boundary conditions on our graviton wave functions. And if these boundary conditions are time dependent, then the vacuum of the bulk is time dependent, and that leads to particle creation, like you all know it from electrodynamics. If you have a volume which is bounded by, for example, two metal plates, then the Casimir energy leads to an attraction of these two metal plates, which has been measured. If you now move one of these two metal plates, for example, in an oscillatory behavior, then that will lead, in principle, to the generation of photons. This effect has been calculated so far, but not yet been measured. People are trying to measure it, but they have not yet succeeded because the measurement is very difficult. And in the same way, the scenario I will be discussing will be the following. You'll have an anti-de Sitter space. This is the extra dimension. Here I suppose a static brane to sit, whereas this one is the physical brane, and we shall consider one motion. This brane approaches the static brane and then bounces back, and we'll calculate how many gravitons are produced by this process. The scale indicated here should be the anti-de Sitter curvature scale, and I will come to more details of this model just in a moment. Now, as we discuss, so the five-dimensional background in quantitative coordinates is conformally flat and is given by this three-factor L over y squared, where L is the curvature, anti-de Sitter curvature radius. The Einstein equation in the bulk relates this curvature radius to the negative bulk cosmological constant. Now, the induced four-dimensional metric, if we now look at our brane, which is at some position yb, which depends on time, so that brane moves with a certain velocity, we find that the induced metric on the brane is given by this expression, where d eta, the conformal time on the brane, is obtained from the conformal time in the bulk just by a boost. And the scale factor is then given by L over the brane position. Now, the analog of the four-dimensional Einstein equations, we only have the bulk Einstein equation, and then we have junction conditions, which are more or less the Einstein equation integrated over the brane, which is kind of singularity. And I have written them down here only in the low energy limit, only if the tension times the energy density is much smaller than the energy density squared. There would be energy density squared corrections to it. If that is true, you find the usual Friedmann equation, as you see here, if you identify this three-factor here with 3 times the four-dimensional gravitational constant, kappa 4. So you have to make this type of identification. And in addition, if you don't want to have a huge cosmological constant also on the brane, which we know the four-dimensional universe has a small cosmological constant, if any at all. So then you have to, the curvature scale and the tension on the brane have to obey this so-called Randall-Sundrum fine-tuning condition. If you want to express it all in terms of length scales, so you say kappa 5, which is the fundamental bulk gravitational constant, would be some string scale cubed. Kappa 4 is the usual Planck scale squared. Then you can get the following relation between these. The Randall-Sundrum fine-tuning condition requires the following relation between the string scale and the four-dimensional Planck scale, and the ABS curvature scale, which is given here. So you see you can have, if this curvature scale is much larger than the string scale, you will get a Planck scale which is much smaller than the string scale, and you can attempt to at least mildden the usual hierarchy problem between the electroweak scale and the Planck scale. Because here in this model, of course, the Planck scale is a derived scale, it's not a fundamental quantity. It's a scale given by this brain tension and the fundamental five-dimensional string scale. Okay, now we consider the following situation. As I have already said before, we have here a static brain, and that's the physical brain, which we assume to be approaching the static brain, and then turning around. When it approaches the static brain, the universe is contracting, and when it turns around and goes away from it, the universe is expanding again. So it's an equinoxic type universe, and we just want to see whether the dynamical Casimir effect, graviton production on this dynamical space-time leads to some observable consequences, can put some limits on such a scenario. Because that's usually what we want to do, right? To see whether there is some observable, if we have some type of model which we propose, we want to derive observable consequences and calculate them and see whether we can rule it out. So let's see whether one can rule out such a model by its by the gravitons which are produced. The background for maybe I should say something about the bounds which I will have to induce, right? At some point I will have to this physical brain to turn around. And I shall not model that in any detail in saying I know how exactly this happens, but I shall model it as just a kink in the scale factor. And as we shall see, due to that kink in the scale factor, there will be actually a divergent particle production. So what we will have to do is to identify the energy scale at which this kink is rounded off. And we assume that this is the string scale, that at the string scale there is some additional physics coming in, which is not described here just by five-dimensional GR, but which goes beyond, and which leads to a turnaround of this brain, so which changes contraction to expansion, which leads to these bounds or to the Big Bang. So that is not going to be modeled, but we will just cut off all particle production above a certain scale by assuming there is nothing produced on scales higher than that. So with this, assuming this kink, the radiation-dominated background solution at low energies is just given by a linear scale factor, which where we assume that at t equals 0 the bounds happen, and at t equals 0 the value of the scale factor is given by Tv over L. So y then, which is just L over the scale factor, is given by this expression. The velocity as a function of time then jumps at t equals 0, it changes sign. And this solution is good if the velocity is much less than 1. So the maximum velocity is the one when t is equal to 0, is given by yb at 0 over L squared, or t over t, L over tb squared, and that has to be much less than 1, so that our approximation is valid. If not, there are v squared corrections to everything. Now we want to consider tensor perturbations in this background, which is modify the four-dimensional metric. So this is our four-dimensional tensors, as you see, not five-dimensional ones, just the usual gravitons. We could also consider the other five-dimensional graviton modes, and we would obtain exactly the same equations for them. For simplicity, we just consider that one, and actually they satisfy just simple wave equation, box h equals 0 in ADS5. The boundary conditions at low energy, here I again make an approximation that we can neglect the velocity term, which will also be there in this boundary condition, are Neumann boundary conditions. And if we can assume these boundary conditions, then that problem is just an ordinary Sturm-Liouville problem, and we have a complete orthonormal set of instantaneous solutions of the spatial part of the equations, the y part of the equations. As you see here, K has been Fourier transformed, so the three-dimensional spatial Laplacian has been replaced by a factor K squared. So these are these instantaneous solutions, spatial solutions. There is a constant mode, that's the zero mode. You see that does not depend on y, it depends on the boundaries only, and the y and the boundaries on time. Then there are massive modes, the Kaluza-Klein modes, which are given more or less by basic functions. Here with some mass term mi. The boundary conditions and some normalization constant here. The boundary conditions at the brane are satisfied because the derivative of C2 is just C1, and you see here by construction C1 vanishes on the brane. And the boundary condition at on the static brane requires that C1 on the static brane vanishes as well, and that leads to the quantization of the masses. Not all masses satisfy these conditions, so we have a quantized tower of Kaluza-Klein masses which satisfy these boundary conditions. Now we make, as usual, our ansatz is some function of time times this instantaneous mode function, which satisfies the spatial part of our wave equation with some mass term m squared, m alpha squared. And now we can derive an equation of motion for these three factors, q alpha, right? If they would be constant, we would have no particle creation. Nothing would really happen. Or if they would just be harmonic exponentials, just harmonic functions, then we would have nothing happening. And here you see we have a wave equation with a mass term m alpha, which is this mass term determined by this condition. And you see this mass term will be time dependent because C1 is time dependent over the fact that YB is time dependent. So this mass is already time dependent. But then there will be another coupling term. These matrices M and N are matrices which are actually given by integrals over the mode function. So they are time dependent. And M is antisymmetric. So you see this first term is what you all know from inflation, where we have more or less a harmonic oscillator with a time-dependent frequency, which always leads to particle creation, right? But here we have additional effects which come from the fact that in y direction our space is non-trivial. So we have coupling of different modes. The different modes couple to each other. These matrices M here are just integrals which have to be computed numerically over the instantaneous solutions. So we have two effects. We have, as in inflation, a varying frequency, and we have a coupling of all modes to all others, which makes this problem numerically harder to solve. We cannot solve just one mode by itself. We have to solve them all together. Actually, if the time becomes, when time goes to plus or minus infinity, the masses become constant and are roughly given by this expression here, and nothing happens anymore. So that's the reason why this problem is relatively easy to tackle. At very early times in the past, it's more or less a free system, and very late in the future it will be a free system, so it's really like a scattering process. In between something is happening, and at the beginning and at the end, nothing, things return to more or less constant. So if I calculate the zero mode, so that's more or less the amplitude of the graviton on the brane, you see that goes like 1 over A. So if I will calculate h dot squared on the brane, that will go like 1 over A to the 4, as I expected for radiation to behave. So that's going to be the massless graviton. But what is surprising is actually that the Kaluza-Klein modes do not decay like 1 over A cubed, as you might think, massive particles, as soon as the energy or the Hubble parameter is below, or the temperature is below the mass of this particle, then the energy density in the particles will decay like 1 over A cubed. This will not be the case, and the reason mainly comes from this, not only, but mainly comes from this normalization of the wave functions. These normalized wave functions decay like 1 over A squared on the brane. This is actually a manifestation of the localization of gravity in ADS. Whatever the Kaluza-Klein modes are manifestations of the 5-dimensionality of space-time, and they are repulsed away from the brane. So the concentration of these wave functions on the brane gets lower and lower as time goes on. Now we will come back to the implications of that later, but now we just quantize this function q of t. We assume that initially we are in some vacuum state. We expand our q operator in terms of creation and annihilation operators, and then we evolve it in time. So at some arbitrary time, it is just some superposition of the initial states with some functions epsilon of alpha and beta, which depend on alpha and beta to get q hat of alpha. And at late times, it is given by some out creation and annihilation operators, which are obtained by the in operators via some Pogolyubov transformation. And what we are really interested in, and what I will show you next, is the particle number, right? We want to calculate what is the particle number at late times once it stops changing. And that is just if we are sufficiently late after the bounds. So what we have done to calculate this quantity, we just have to calculate these functions epsilon, and they obey the classical equation for Q. So we just have to do a numerical integration of the system of coupled differential equations. Of course, to do this, we have to cut at some value alpha. We have to cut our system, and I will show you the dependence of the result on the cutoff. Here you see numerical result for the graviton number density for the zero mode. Here you see that really something is happening once we approach these bounds, and after bounds the particle number is more or less constant. The same thing happens with the KK modes, and what we actually find that these KK modes are more or less entirely generated by their coupling to the zero mode. So the zero mode loses part of its energy, and that I think is what is responsible for this dip here mainly, because it generates all these massive modes. If one neglects the coupling to the zero mode of these KK gravitons, the amplitude drops by more than 2 orders of magnitude of the generated Kaluza-Klein modes. So what do we want to calculate once we have solved these equations? We want to calculate the power spectrum from the gravitons. Here, either the sum over all masses, or what we are more interested in, and what I will show later, is only the zero mode, alpha equals 0. We want to calculate the energy density in massless gravitons and the energy density in massive modes. And due to the normalization of the wave functions of the massive Kaluza-Klein modes, we see that the massive energy density in massive modes actually scales like 1 over A to the 6. It doesn't scale as we would naively think like 1 over A cubed as a massive, ordinary massive particle. There is an additional factor, 1 over A, coming from the mass of the Kaluza-Klein mode, because this mass here, which we obtained, which is nothing else than the momentum in the transverse direction, is actually a co-moving mass, so it scales like 1 over A, because that's the mass with respect to the co-moving y-coordinate, the momentum with respect to the co-moving y-coordinate. This gives us one factor 1 over A here, and another factor 1 over A squared comes from the normalization, that actually the wave function which describes this Kaluza-Klein mode is pushed away from the brain, has less and less support on the brains. So this makes this Kaluza-Klein mode scale like 1 over A to the 6, which means Kaluza-Klein particles from a warped brain world like that one, which confines gravity onto the brain, cannot play the role of dark matter. It doesn't redshift in the connected wave. It doesn't redshift like matter. It redshifts like some stiff component. These are our numerical solutions, which we have compared with analytic solutions in this regime, and which are in very good agreement. Here we see the power spectrum of the zero mode for different, as a function of time, for different values of the wave number. And we see on super horizon scales it has some amplitude, and then it decays and oscillates as it enters the horizon. And you also see, if you look at these numbers, that the amplitude actually increases with increasing wave number. So it's not a stereo-invariant spectrum. Actually, we will see it's a spectrum which scales like k squared. Here you see the number of Kaluza-Klein modes at given wave number, also compared with an analytical calculation which has no fitting number in it. So we think we really understand what happens here. In this analytical calculation, we only took into account the coupling of the Kaluza-Klein modes to the zero modes and nothing else. Not the time dependence of the frequency, etc. Self-coupling, nothing else. And you see it gives a relatively good fit, at least until roughly Kaluza-Klein mass of order of unity. This is all in scales of L, where L is the ADS curvature scale. And we also understand why here our fit is no longer very valid, because you might think that this is a convergence problem and that these numbers would converge up here, but that's actually not true. They do not. Even if we increase the number at which here the black dots are cut at the Kaluza-Klein mode 40, etc., etc. The blue ones only at 80, but they do not approach this point here. The analytical approximation breaks down for Kaluza-Klein masses larger than 1. At very high frequencies, omega, which is square root of k squared over m squared, larger than 1, the thing which these Kaluza-Klein modes mainly feel is the kink. For a pure kink, where we have constant velocity of the brain, so no particle creation, and then just a sine flip of the velocity, and then it goes on again, one can solve the system analytically and actually finds that the particle number should go like v squared over the frequency, and that's exactly what we see for these large frequencies. So if there would be a perfect kink, the total particle number, which would be the sum of these, and then the integral overall over three-dimensional Fourier space would be divergent, right? The total particle density. But this is, of course, only the case because we assume here a perfect kink. So we allow all frequencies to be generated, arbitrarily high frequencies to be generated, and actually we have to cut off the frequency. And the result depends very strongly on what we choose for this cutoff. What we choose is the string scale. And if we do that, that's what we find. We find a power spectrum for the zero mode, which goes like k squared, so not a stereo-invariant spectrum, and whose amplitude is on Kobe scales or so, on C and D scales is much too low to see anything. But we have energy density in these gravitons, which of course is dominated by the upper cutoff in Fourier space, which is given by this expression. Or if we divide it by the radiation energy density, we find that the energy density in massless gravitons is just given by the velocity, maximal velocity of the brane times the radiation density, which is not such a surprising result. So the nucleosynthesis band requires that this maximal brane velocity be less than about 0.1, which means that our low velocity approximation is probably not so bad if we anyway have to require this. Now, even more interesting are the Kaluza-Klein modes. Their energy density, as you see, it scales like 1 over 8 to the 6, but it can be very well approximated by this expression for all velocities, which you might consider. And if you divide it by the radiation energy density, now depends, of course, at which value of the scale factor you are going to do that, and you want to do it at very early time, so right after the bounds, where this ratio is going to be highest, and you find that it is given by roughly 100 times dB squared times this factor here, which is the curvature scale divided by the position of the static brane times the curvature scale divided by the string scale squared. So we see that if we want this number here to be much smaller than 1, so that we may neglect the influence of these Kaluza-Klein modes onto the evolution of the background, we need quite drastic criteria. We really need that either this ratio here is much smaller than the ratio of the string scale to the ABS curvature scale, or we need a very low brane velocity. Just as an example, if you would want to solve the hierarchy problem and assume a curvature scale of 0.1 millimeter and solve it or address it, let's say, take the maximum curvature scale which you are still allowed to take, then you have a string scale which is about 10 to the 9 GeV inverse. You find that the static brane must be at some huge distance from the physical brane, which is a bit unnatural, to say the least. On the other hand, as we have seen before, the maximal velocity is actually given by YV over L. So if we want that to be much smaller than 1, we need that the physical brane has to be positioned closer to the Cauchy horizon than L inside. So to draw some conclusions, I have shown you that if you have a brane world where expansion is mimicked by a brane moving through a vast higher dimensional space, you have the creation of gravitons via dynamical Casimir effect. You generate bulk modes, whatever your bulk modes are. And for an ABS bulk, the nucleosynthesis bound on gravity waves requires that the speed of the physical brane be always sufficiently small. And Kaluza-Klein gravitons scale like stiff matter and cannot be dark matter in ABS5 brane world. If we would have some other bulk geometry with some other bulk fields, I think as long as we want that gravity is confined on the brane, then on the brane we have something like 4-dimensional gravity. We need that the 5-dimensional aspects, like Kaluza-Klein mode, have wave functions which get pushed away from the brane and therefore lead to an additional suppression of the energy density in these modes. And even though this may not be 8 to the 6, I think if they would scale with a steeper power law than with 1 over 8 cubed. And I think that would survive in all type of warped brane worlds. Of course not if your bulk is just a cylinder. And I think the previous slide showed that for interesting brane worlds, I think back reaction from Kaluza-Klein gravitons on the evolution of the space-time is probably not negligible and has to be taken into account. The one brane case we have looked at a couple of years ago, and there one finds if you have only one brane, one finds that graviton generation is nearly negligible. You have, if you look at the model we have now studied and just let the static brane go to infinity, most of it actually disappears and you have no serious amount of graviton production. Thank you.
In the archive versions of this, you mentioned that this was motivated in part by the ironic universe scenario, where there's been this controversy, right? Where on one hand, Steinhardt and Turok et al. Argue that you get a spectral index of order 1, consistent with what Lyman Page told us about. Now, on the other hand, Mattia Zaleaga and Carlo Cremonelli et al. Argue that you get n equals 3. So, since you've done these very careful calculations now, what's your opinion of it?
Okay, I think that this has been more or less settled now that you do get n equals 3. I think there is has been some work a couple of years ago. But you see here, I look at the gravitons only.
Does that mean the whole model is dead, in your opinion?
You see, if n is equal to 3, this means that this model, as proposed in that way, does not produce any fluctuations on Kobe scale, right? Because it just means because you have to normalize the spectrum at the small scale, so there is nothing left on large scales. This means if you want to have the correct fluctuations, you have to invent another mechanism to make them.
Right.
The one which they propose can't do it. So, but maybe there is some other solution to that problem. So, but here, of course, we are just studying one aspect, which is this particle creation, which should happen more or less in all bouncing cosmologies. So we are not looking at the scalar perturbation equations, and then the ones, I mean, in this bouncing model, in this epirotic model from Steinhardt and Turok and company, there have been a couple of things which have not been studied. For example, all the bulk modes have not been studied yet, and it is not clear what the bulk is doing. They haven't really specified that in any detail. Here I take a very specific bulk, ADS5. I think they think more of a Minkowski type bulk, but they don't really specify it because they try to reduce everything on degrees of freedom which you have on the brain, which is a bit doubtful, and usually this cannot be done.
Maybe I missed the point, but you could say that the kink occurs when some scale reaches the free-type value. But I tend to see how you get to that high scale in your model because the ADS radius is large, right? And the velocity is small. So where do you get this high curvature at the kink?
Okay. I mean, that's of course a very justified question about which we thought for a while. It might be, I mean, we have seen we cannot, at the beginning when we started this work, we thought that just the physical and the static brane approach each other very closely and then something is happening. But since they cannot approach each other very closely because of these limits which we have, this cannot be the case. So something which could maybe happen is just that the energy density on the brain becomes relatively large, and that then the scalar the energy density on the brain behaves in a different way and makes gravity become repulsive, that we could have a bounce. But I agree, it's not clear to me how this bounce will really happen. We just assumed it happens without, and assumed, of course, that it happens in a finite time scale. Now we assume that time scale to be roughly the string scale. If it would be another scale, everything would change.